Hello, so good afternoon everyone. So once again, my name is Charleston. So my background is not really about electrical grids, electrical engineering. So my background is more on microwave theory, radio frequency engineering. So why am I presenting here in this session of power and energy? Okay, so I'll give you an outline of my presentation. It's divided into 5 parts. I'll give you why am I part of this session, and how do we calculate efficiency in this long-range wireless power transfer? What are the dynamic beam focusing techniques, which is the focus of this presentation, some performance comparison via simulation, and a summary of this presentation. Okay, so first, why long-range wireless power transfer? The motivation is really because of space-based solar power. So what it is you collect solar energy from space and beam it down back to Earth in a focused beam. So the beam focusing here is at microwave frequency. It's a very large structure. So if you want a 90% efficiency, beam collection efficiency, your satellite at geostationary orbit is around 2.5 kilometers by 2.5 kilometers in size. So that's 1 billion antenna elements that you need to control. And this size is estimated to supply 1.6 gigawatts of power. Okay, so this is an overview of its different subsystems, and what I want to focus here is the DC to microwave block and direct antenna block, at least the interface between them. How do we transfer power from a long distance? Okay, so just a review. So when you talk about electromagnetic wave propagation, you can roughly divide it into 3 zones. The far field, where communication systems happen. The reactive near field, where we do some circuit theory approximations. In between them is called the radiative near field, where long-range wireless power transfer is envisioned to operate. So that is the focus of this, of the long-range wireless power transfer technologies. So it is dependent on the frequency of operation, or the wavelength of operation, and the size of the antenna. So the bigger your antenna, the longer distance you're able to transmit. The larger distance is your radiative near field zone. Okay? So the challenge of implementing this is that if you have a big antenna, you subdivide it into antenna elements. And you have to control the amplitude and phase of each antenna element to focus power towards a specific area in the radiative near field zone. Okay, so at geostationary orbit, that's at least 1.5 billion antennas. So what can be an appropriate beam control method for this scale? So before we go there, let's look at how we compute for the wireless power transfer efficiency. Okay, so this is the framework that we use to calculate the efficiency of wireless power transfer. So we base it on what we call scattering parameters. Because we're dealing with waves, we use the scattering parameters to characterize the wireless power transfer. So what it is at each antenna, you have a voltage that you measure. You can decompose it into its forward component and backward component. And you can relate these components using the S parameters. Okay, so the matrix equation there is the relationship between your backscattering and the input to your channel. Okay, so this is just for 2 antennas. We can extend this concept to multiple antennas. So it's a big system already. So there's one side is the receiver. Some parts of it is free space. One side is a generator. Other parts of it is the free space. And you can ultimately form this big matrix to relate the received energy and the energy you put in the system. And quite simply, the efficiency is just, if you have the voltage vector of, you measure at your port 1B here, and you transmit power using V to F, the efficiency is what you see here. And simplifying it further based on S parameters, we get this box expression, which is also the Rayleigh quotient, as we call it. So this Rayleigh quotient can be found in quantum physics, this formulation. And the maximum value, the optimum value of this, is the maximum eigenvalue of the matrix that you see here, which is defined by your channel. So this S21, Hermitian S21, is dependent on your antennas, the characteristics of your channel, and all of that. It factors everything into this, this matrix right here. Okay, so If we're talking about eigenvalues, we have eigenvectors. So eigenvectors, we have transmission modes that we can define, and there's one eigenvector that maximizes the wireless power transfer efficiency. Okay. So now let's look at the techniques developed to achieve this or to find this maximum eigenvalue condition. So one technique is you just detect your receiver using a sensor. It could be a camera. Your receiver could have a GPS sensor, and it reports its position. And your controller just computes using classical beamforming computations to point the beam towards the receiver. Another approach is you release a pilot signal from your receiver, and your transmitter, your power generator, will train itself to point towards the receiver. And the last approach is you use your telemetry. You send back some data, maybe the power you receive, and then you optimize the beam based on the data that you get. Okay, so those are the three broad approaches towards wireless power transfer. Okay, so these are the summary of all the works that we've reviewed for the different methods. So what type are they? Basically, you can see here that there's a trade-off between your feedback, your settling time, how fast your system settles, compared to achieving the maximum possible efficiency. So if you want to be fast, it's going to be hard to achieve maximum possible efficiency. But if you have enough time to adjust, you're able to transmit in the maximum efficiency mode. Okay? So let's have some performance comparison. Okay, so what we did is we simulated a moving antennas or a moving obstruction in an electromagnetic simulator. Okay, so the first one is the antenna is revolving around the other. The second one is there's an obstruction passing through the space between the two antennas. Okay, so this is a scaled version of this long-range wireless power transfer. It's still in the radiative near field, rather. So you compute the S parameters for each case, and then incorporate it in a time domain simulation. So this is the block diagram we implemented in Simulink. So we are able to model the S parameters, the wireless channel, based on the electromagnetic simulation results. Okay, so basically the S parameters just define a gain and a phase delay or a time delay to each of your inputs, and then you just sum them towards your receiver. So this is the time domain model. Okay? So first, we simulated the case where the channel is not moving, but the antennas are misaligned, okay, and measured the settling time and the steady state efficiency of each of the different types of wireless power transfer techniques, beamforming techniques rather. So as I've asserted earlier, the position tracking type and the pilot signal or the pilot signal beam training type can settle very fast. In this case, compared to the others, it settles at 0.06 microseconds. If you're going to use some feedback-based methods where you iterate over different data, maybe you will be slower, maybe 2.56 microseconds at the worst. Okay, but when you look at the efficiency, all the feedback-based methods are able to achieve the maximum possible efficiency afforded by the channel condition. Okay? So the trade-off that we asserted earlier is observed in this simulation results. So what happens now if we put it in dynamic channels? So when the channel is moving, the maximum efficiency also changes over time. Okay, so for the first case on your left, this is the revolving antenna case. It is maximum when the antennas are in the best alignment case. So as you can see here, from the worst alignment, it revolves towards the best alignment case. And you can see that the efficiency of all cases increases. That's the graph on the upper left. So the lower left graph is just the ratio of the efficiency with the theoretical maximum. If you look at the graphs, you can see that for the position tracking type and the pilot signal type, they're not able to achieve maximum efficiency in most of the cases. But for the for the iterative types or the feedback-based types, you're able to see that it can achieve the maximum possible efficiency in that case. Same is what happens when there's a passing obstruction. So what happens here is that initially there's no obstruction. So this is the graph on your upper right. Initially there is no obstruction and then it passes through until it's completely in the middle. So when there's an obstruction, you can see a decrease in efficiency. Okay, and then if you look at all the cases of all the different types of beamforming techniques, it's still the same. Okay, so what happens is the feedback-based types are able to achieve maximum efficiency that is afforded by the channel conditions at that time, okay, compared to your position tracking type and your pilot signal type. Okay? So to summarize this presentation, okay, so if you want to transmit in long range, you need a large antenna composed of small antenna elements, and you must be able to control them, okay? So we introduced 3 broad types of techniques to control the beam, and we observe a trade-off between trying to achieve maximum efficiency afforded by the channel and the settling time. So the slower you are, the more you're able to achieve maximum efficiency. Okay? So some future works. So now next is to how do we improve the efficiency? So in this study, we only focused on the channel conditions, but there are techniques to increase the efficiency by improving your antenna design. Okay? And also there's also to implement a stabilization in one of the feedback-based types, and possibly to go smaller first, not space-based. So go smaller first and do it in applications like mobile charging or EV charging. So yes, that's the end of my presentation. So any questions?
Sige, Charleston, kung wala pa silang tanong, where can they read your articles pagkatapos itong session na ito? Search na lang kami ng...
So you can actually read some publications that we made for this, for all of these studies. You can look at my Google Scholar page. It's nandun halos lahat. Yung mga recent publications ko from 2022 to 2024. So a lot of it is published. Yun din yung pinresent ko dito halos.
Thank you, Charleston. Kulang yung 15 minutes para sa PJ, Sir PJ ko sa question over there.
One question, Charleston. Thank you for the presentation. So, yung minention mo kanina na 1.5 billion antennas, no? And it's supposed to be in the near field, well, radiating near field.
Yes.
Ano yung, para makuha yung size na yun ng array, anong orbit yung ina-assume dito?
So, ina-assume namin na yung orbit is at 36,000 kilometers elevation at 5.8 gigahertz. So, it's at half wavelength spacing yung antennas. So, you're able to get at least 1.5 billion antennas. Yes. I remember correctly, yes.
Sige, usap na tayo mamaya. Thank you.
Thank you, PJ. Kasi doon sabi ko rin, kulang yung oras para i-discuss ito nga ito. We actually invite you to join the graduate program sa EEE, magiging teacher niyo sa Charleston. Charleston, before you go down, we give him this certificate of appreciation, which you present to Charleston. Charleston Ambatali for sharing his insight and work on dynamic beam focusing techniques in long-range wireless power transfer during NISCON 2024, given this 18th day of July, signed by Dr. Lutria, Director of EEI. Thank you.